All right, welcome to our presentation. I'm Brian Shadron, here with Danny, Jackie, Jack, Cody, Paul, Derek, and Din. And we'll be updating you on our progress with REEF this spring semester 2012 and this past fall semester. And our advisor is Dr. Walter O'Brien. This presentation will focus mostly on our detailed design, but we're also going to start with our conceptual design completion. This is going to include some of our Homer economic analysis, as well as our final system architecture selection. That's going to be followed by our engineering plan. That's going to talk about a few of our design factors, as well as some of the specific technologies that we cover, or that we are implementing with our architecture. Next, we're going to go over our business plan, and that's going to include a more detailed cost analysis, as well as our business outline and the way our business would be set up. And then finally, we're going to conclude with a Simulink, or our Simulink model, as well as a new technology that we found called DO that's going to help us model the grid integration on Tonga. So just as a refresh, the mission of Tonga is that we are going to design an autonomous renewable energy system for community. Basically, we want it to be economical, socially acceptable, and practical. But what does that really mean? A couple factors that we're looking at are that we want to design a system for a specific community. So we're going to look at a lot of the different factors in that specific place and implement them into our design. And we're going to use renewable resources. So we want to, a lot of the areas that we're looking at are highly dependent on diesel generation. So we want to reduce the price of electricity with those renewables as well. And two other factors are that we want to provide a commercially competitive solution, because a lot of these projects need investors to get off the ground. Then also we're going to use, as I said before, resources present at that specific location, and that may change if we were to do projects in the future. So just kind of as a recap, we wanted to select our location, identify resources at that location, and then with those two factors, design a system that would be implemented well there. And then finally, with all those factors, we'll present a comprehensive project plan to our site. And the site that we selected was Tonga. It has a population of about 104,000 people, and currently has an energy demand of 9.6 megawatts, but we expect that to increase with increased demand and increased population. So our project plan will have a higher energy output than that. And then their electrical cost currently is 88 cents per kilowatt hour, but at the time of our fall presentation, that was at 57 cents a kilowatt hour, so that just shows how dependent they are on the diesel generation. So some of the resources that we're looking at currently are solar, biomass, wind, and tidal power. And also we picked Tonga, not specifically, but a big reason is the Tonga Energy Roadmap, which is a document put out by the government saying that they want to reach 50% renewable resources out of their total energy by 2015 and 100% by 2020. So just as a recap for what we did this past fall semester, we had the final site selection of Tonga, and on Tonga we researched those specific technologies to get down to the ones that we wanted to use. We ran an initial Homer cost analysis, which took into account the technologies and the cost of those technologies to find a good combination, or the best combinations. And then also we formed the simulation team so they could start investigating Simulink so that we could get a jump on that in the spring semester. And then finally in the spring semester, we've been working on a more detailed cost analysis. We've simplified our Simulink model to not include the grid integration, and we want to use the DO software to model that grid integration. We've continued to work on our business plan and model, and also identified factors that we wanted to use in our engineering plan. And I'm going to pass it off to Cody to talk about our conceptual design and system architecture.
Thank you, Brian. As you mentioned, we began the semester concluding our work on the conceptual design of our system, that is picking the system architecture, what combination of renewable energy resources we wanted to use, and in what proportions we wanted to implement those. And to do that, we've been using this Homer software from the National Renewable Energy Labs. This software has been widely accepted in the renewable energy community, and has been helping us evaluate both the economic and technical feasibility of our various options. We've also combined this with some of our expertise that we've gained over the course of the year doing research on these different resources and technologies to come up with a number of different options for renewable energy technologies that could be feasibly used on Tonga. So we've analyzed several different categories of resources. The first is wave and tidal power. Among the options we analyzed there were CETA, which is an underwater fan system, but that proved to be entirely too expensive for our purposes. Next was Osprey, which is also a half submerged, half above the waterline system that provides a mooring for wind turbines, but that technology is just not mature enough at this point for us to feel comfortable including it in our plan. So that's also been eliminated from consideration, as has the Limpet system, which is a shore-based installation. However, Tonga has some geology, specifically some offshore reefs, that limit the energy potential of that particular type of wave energy. So we decided to use a Palamas system, which floats above the surface of the water and will be discussed later on in this presentation in the new engineer plan. We next looked at wind turbines, ranging in size from 1.5 megawatt GE turbine up to 1.8 megawatt Vestas turbine. And from our economic analysis, we concluded that neither the GE nor the Vestas V90 was the best option, but rather that the Vestas V82 would fit our purposes well because it is optimized for the type of wind speeds that we expect to see on Tonga. We next analyzed our options for solar power and looked at these two main categories, concentrated solar power and photovoltaic cells, which you're most familiar with. We realized that for the economics of a CSP system to work, we would need a scale much larger than what we have on Tonga. Therefore, we've eliminated that and chosen to go with the PV system. And then finally, we looked at different storage alternatives. We first looked at hydrogen, and from the round-trip conversion efficiencies of that, we realized that that's not where we need it to be yet to implement in the system. So we eliminated hydrogen. Also compressed air. Tonga doesn't have the geology necessary in order to be able to do that. So compressed air is out, as is pumped hydro, because there's not enough elevation change to store energy there, which left us with batteries, which are still a very good option and have been commercially used. So once we picked the resources we were going to use, we had to figure out how to make the transition from where they are now, which is 100% diesel, to where we want to be, which is 100% renewable. And to do that, we had to consider not only where they're at right now, but also the projections for demand and also their fuel costs going into the future. So Tonga Power Limited, which is the power authority on Tonga, has published their expectations of the fuel they expect to use and what they expect it to cost over the next few years. And this shows their projections, a range of different scenarios from a low cost to a high cost scenario. This black line here shows, in general, the electricity demand, how they expect that to grow over the coming decade. So we can see we have some modest growth to account for, which we've taken into account as we've developed our plan. And what we did is we took technical data from Tonga Power Limited, incorporated that into our Homer model to analyze how to combine what they already have with the systems we want to put in and move them towards 100% renewable. So the result of this process was a two-phase strategy, moving Tonga from 100% diesel to 100% renewable in two stages, the first of which, mirroring their energy roadmap, is 50% renewable, which will encompass years 1 through 10 of this project. As you can see here, this includes 50% diesel, and then roughly split evenly between solar and wind technology for the remaining half. This will be 8 megawatts of PV generation and 2 Vestas V82 wind turbines, along with 800 battery units from A123, which will provide 6 hours of energy autonomy. And this plan will also save Tonga the amount of money they were planning to spend on new diesel generation. It will allow us to kind of ease into this to develop the expertise on Tonga. It will allow time for wave technology to mature and be even more cost effective, we hope, for the second half of the project. And this will also meet their goal of getting to 50% renewable energy by 2015. Phase 2, we go all the way, 100% renewable. And after 10 years, we're going to look at developments in wave power technology. How fast is the Palamas system coming along? How much have the costs come down? And then we're going to decide based on that. What we'd like to do is include the Palamas system to account for the base generation you lose when you take the diesel out, and that's what we expect to be able to do. However, if the wave technology turns out to not develop as much as we'd like, or to be more expensive than we'd like in the future, we have determined that we can still meet all the energy needs for Tonga with additional solar and wind installations and still do this in an economical way. So why is wave energy so important? As you can see here, as the size of the wave system included increases, the cost of electricity for the system decreases dramatically. So this is why we are so hoping to be able to include the Palema system, and that's what we expect to be able to include it. However, we're going to take a wait-and-see approach based on the fact that wave technology is still very young. So now Jack is going to talk to you a little bit more about the engineering plans and the details of how we are going to make this happen.
Thank you, Cody. As part of our proposal to the Kingdom of Tonga, we've also put together an engineering plan. As Brian mentioned earlier, Tonga is currently supplied with 100% imported diesel. Their electrical grid is supplied from a diesel power generator with a 12.7 megawatt capacity. Now, as an initiative to reduce the dependency on oil, the Tonga Energy Roadmap was initiated, and as the first step, they've begun their construction on a 0.75 megawatt solar farm. Our plan is that our system will integrate into the current grid, as well as function in conjunction with the solar farm. We've done several preliminary environmental researches looking into several important factors that's going to affect our system. One of the studies that we found, it was a study done which evaluates the vulnerability of Tonga by cyclones and flooding. As you may know, Tonga is located in the South Pacific in what's known as the cyclone belt. So on average, Tonga experiences about 2 cyclones per year. And these flooding brought on by the cyclones will inevitably help dictate the location of the system. As you can see in this figure, with every meter sea level rise, the land area loss becomes more and more significant. In addition to land area loss due to flooding, several beaches in Tonga also experiences beach erosion due to over-farming. Due to the rapid increase in development, sand resources has been really scarce for Tonga. These beaches, these exposed bedrock on these beaches have been very unsuitable for tourism. However, for our purposes, they can potentially serve as foundations for our wind turbine, as these locations often provide the best wind conditions. Right here you can see a wind map study done by an organization called Winergy. As you would expect, on the coastline of the island, we would see the most favorable wind conditions. The part that we're interested at is the eastern shore, as highlighted by the dark orange areas. The study has shown that in these areas we'll experience anywhere between 7 to 8 meters per second wind speed. Also, in addition to favorable wind conditions, these areas also have a higher elevation as to